Atomic energy levels. An atom of an element is generally made up of electrons, protons, and neutrons. The only exception is the hydrogen atom, which possesses one electron and one proton, but no neutron. While an electron is negatively charged, the proton is a positively charged particle. The charge of a proton is numerically equal to that of an electron, but the mass of a proton is 1837 times that of an electron. A neutron is a neutral particle having a mass nearly equal to the proton mass, because the protons and the neutrons carry practically the entire mass of the atom. They remain almost immobile in a region called the atomic nucleus. The electrons revolve around the nucleus in definite orbits, which are circular or elliptical. The motion is analogous to that of planets around the sun. The atom is electrically neutral because the number of orbital electrons is equal to the number of protons in the nucleus. The atom of one element differs from that of another due to the differing numbers of protons, neutrons, and electrons in the atom. In the Bohr atomic model, the electrons are assumed to move above the nucleus in certain discrete circular orbits without radiating any energy. In any orbit, the angular momentum of the electron is equal to an integral multiple of h by 2 pi, where h is Planck's constant, that is equals to 6.62 into 10 to the power minus 34 joule second. The integral number n has values 1, 2, 3, etc. For different orbits, the higher the value of n, the larger the radius of the orbit. The allowable discrete value of n, so that all energies are not permitted for the electrons. The electrons can have only certain discrete energies corresponding to the different integral value of n. In other words, the electron energy is quantized. The allowable energies are represented by horizontal lines in a diagram called the energy level diagram of the atom. Figure 1.21 shows such a diagram. When an electron jumps from a higher energy level EH to a lower energy level EL, an electromagnetic radiation of frequency nu is emitted, that nu equals to EH minus EL divided by H, where H being Planck's constant. On the contrary, on observing a photon of energy h nu, an electron initially at the energy state EL can move to the energy state EH. An electron normally occupies the lowest energy state called the ground level. The other higher lying energy levels are called the exciter levels of the atom. By observing more and more energies, an electron can move into excited states which are farther and farther away from the nucleus. If the energy is sufficiently high, the electron can overcome the attraction of the nucleus and gets detached from the atom. The energy required for this to occur is known as the ionization potential. The energy required for this to occur is known as the ionization potential. The energy level corresponding to n equals to infinity in figure 1.1 represents the ionization level. As the electrons are electrostatically attracted by the positively charged nucleus, the allowed energies for the electrons are negative. The ionization level represents the zero level of energy. The ionization level represents the zero level of energy. The energies become more and more negative with decreasing value of n. The energies become more and more negative with decreasing value of n. The wavelengths emitted from the atom due to electronic transitions from higher energy states to lower one give the spectral lines. The spectral lines characterizing the atom. To explain the details of the spectral line of some elements, improvements over the simple Bohr model have been made. Quantum mechanical treatments have introduced 4 quantum numbers designed by N, L, ML, and MS. The quantum numbers can take the following values. N can be 1, 2, 3, and L can be 0, 1, 2 up to n minus 1. ML equals to 0 plus or minus 1 plus or minus 2 up to plus or minus L, and the MS is equals to plus or minus half. The quantum number n, called the principal quantum number, primarily determines the energy of the orbital electrons. The quantum number L measures the angular momentum of the electron and is referred to as the orbital angular momentum quantum number. The number ml gives the splitting of the energies for a given n and l in a magnetic field, and it's called the magnetic quantum number. The quantity ms, known as the spin quantum number, shows that the spin of the electron about its own axis is quantized. The state of an electron in the atom is uniquely specified by the 4 quantum numbers. This is a result of Pauli's exclusion principle. The principle states that no 2 electrons in an electronic system can occupy the same quantum state described by the same set of 4 quantum numbers NL, ML, and MS. The principle states that no 2 electrons in an electronic system can occupy the same quantum state described by the same set of 4 quantum numbers N, L, ML, and MS. Electronic cells. The specific value of the principal quantum number n determines an electronic cell. All the electrons of a given atom having the same value of n belongs to the same electronic cell. The letters K, L, M, N denote the cells for n equals to 1, 2, 3, 4, respectively. The different value of L for a given n define the subcells for the cell. The subcells are represented by S, P, D, F, corresponding to L equals to 0, 1, 2, 3, respectively. For n equals to 1, there are two states corresponding to L equals to 0, ML equals to 0, and MS equals to plus or minus half. These two states are known as 1 states. For n equal to 2, we have two 2 states corresponding to L equal to 0, ML equal to 0, and MS equal to plus or minus half. In addition, there are more 6 states for n equals to 2, L equals to 1, ML equals to minus 1, 0 plus 1, and MS equal to plus or minus half. These are 2p states. The total number of electrons in the K cell is 2, and that in the L cell is 2 plus 6 equals to 8. Similarly, it can be shown that a maximum of 10 electrons can be accommodated in a D subcell, a maximum of 14 electrons in an F subcells, and so on. The number of protons in the nucleus is the atomic number Z. Since the atom is electrically neutral, the number of orbiting electrons is also Z. For sodium, Z equals to 11. The electronic configuration of the sodium atom is 1s2, 2s2, 2p6, 3s1, where the superscripts denote the number of electrons in a particular subcell. Clearly, the sodium